In set 4.6, I'm going to introduce you to some new numbers. So let's consider x squared equals -9. What number makes that true? There aren't any. What about the number 3? 3 times 3 is 9. What about the number -3? -3 times -3 is still 9. Okay. What about 3 and -3? That's not the same number. All right. So this equation has no solution. And that doesn't seem like a big deal to you guys. So what? But it turns out that there are a lot of mathematics situations that rely on stuff like this, especially in electricity, electronics, some other stuff that we're not going to go into. So what we've done is invented a new number. Okay? Now, paying attention there? Uh-huh. So on the number line, the number line starts with 0 in the middle, goes forever in both directions, and there are no gaps. And that number line is called the real number line. Okay? It doesn't mean real because it exists. It's just called the real number line. Okay? And we've kind of dealt with some numbers that are not on the number line. Any decimal you can think of, any fraction, any square root, this number line is made up of fractions, which are called rational numbers, which include whole numbers and negative numbers, and irrational numbers, which are like square roots that don't simplify, and and pi, and there are lots of others. So any number you can think of is on this line, except there are two numbers that we kind of talk about that are not on the number line. Ah, good. The first is infinity. In order to be called a real number, you have to be able to point exactly to the number line, put a dot, and say that's where it goes. Where does infinity go on the number line? Clear to the right. Can I ever go far enough to label infinity? No. All I can do is point an arrow in that direction and say, good luck. Hope you get there. Okay? And if you tried to compute infinity on your calculator will go out 99 numbers, like 99 digits, and then it gives up. Anything after that, it says overload. Okay? And the weird thing about infinity is, let's say I challenged you a race to infinity, and whoever got the closest to infinity wins. So I say on your mark, get set, go, and I take one step, and you run for 40 years. Who is closer to infinity? Neither of you. Because how far am I from infinity if I only take one step? Infinity away. You run for 40 years. How far away from infinity are you? Infinity. So we're the same distance from our goal, which means we tied. So infinity is a really weird number, and there are strange things that happen when you try to treat it like a number, but that's stuff for next year's class, not this class. So infinity is a non-real number. It doesn't mean it doesn't exist, but it's not found on the real number line. Okay? And of course, the other number you know of that is not on the number line is its brother, negative infinity, which is on the left side. It's evil brother, evil twin. Okay. Well, those are two non-real numbers. I'm about to introduce you to a huge group of other numbers that are not on the number line. Okay? And one of them, actually two of them, are found inside x squared equals -9. Okay? So, if it's a real number, good point. I mean, I'm going to introduce you to some numbers that are not real numbers. So, the most basic non-real number is the square root of -1. And up until today, that number has not existed. Okay? So what that's asking is, what number times itself is -1? There isn't one. 1 times 1 is 1. -1 times itself is still 1. What about 1 times -1? It's not the same number, so it doesn't count. Okay? So up until today, this expression did not exist. It is not a real number, which means on the number line, there is nowhere I can point to identify the square root of -1. It doesn't exist. So eventually, mathematicians realized, ooh, that's a problem, because sometimes we need to use these numbers to create situations that we find very, very useful. Electronics being the one that probably influences you the most. But there are lots of other applications too. So what we've done is we have renamed this the number I. Kind of like the number pi. It's represented by a letter, but it is the number 3.1415928, on and on and on and on and on. Right? It's up there. Most of it. No, not even most of it. Part of it. But that number goes on forever. So we represent it by the symbol pi. So the square root of -1 is identified as the number I. Okay? And I'm going to teach you a little bit about how the number I works. Okay? So first off, what if I had the square root of 16? What does that equal? 4. Okay? But what if I had the square root of -16? Well, I'm going to split this, so watch carefully because this is kind of confusing. I'm going to split this into two numbers, the square root of 16 and the square root of -1. That's legal. What is the square root of 16? 4. And what is the square root of -1? I. So the square root of -16 is 4i. Now, what is 4i? That's a little bit hard to explain at the moment. Okay? It is 4 times the square root of -1. Okay? So to begin with, all we're going to do is simplify square roots where there are negatives inside of them. So if I had the square root of -81, what does that equal? It's the square root of 81 times the square root of -1, which is 9i. And that is a non-real number. That number does exist, but it is not found on the number line. If you had a ruler that went forever in both directions, 9i is nowhere on that number list. Okay? What about the square root of -24? Right. And 24 simplifies into 6 and 4, 2 and 3, 2 and 2. Can I bring anything out? Pair of 2's. So 2, and what stays in? So that's a 2 times 3, which is 6. But where does the negative go? In front of? Ooh, so close. Where did I put the I here? After the number. So it actually goes right there. 2i root 6. So the i's, so it's I is the square root of -1. So what we're saying is this is the same as 2 times the square root of -1 times the square root of 6. But instead of writing the square root of -1, we always just write I. Okay, now, where do i's belong? I's go after numbers, after variables, but before square roots. After numbers, after variables, but before square roots. So on the inside, there is no I. On the inside, it's a negative. And we can sort of transfer the negative and the I back and forth if we need to. So I root 24 is the same as the square root of negative 24. On the inside, it's a negative. On the outside, it's an I. Okay? Yeah. Yeah, we're learning some of the rules of simplification today. All right, what if I had the square root of negative 30? That's 3 times 10, 2, and 5. What can I pull out? Almost nothing. There is one thing I can bring out. It's a trick question. The negative, which turns into I. So this is I root 30. Okay? Yes, but the square root of 81 is 9. So you do 9i. Yeah, if it simplifies, simplify it. If it doesn't, like this one didn't have any pairs. So I couldn't make it any easier. Okay, what about the square root of negative 120? So 10 and 12, 2 and 5, 6 and 2, 2 and 3. So I have a pair of 2's. So 2i square root of what's left? Nope. Oh yeah. Yeah, the 6 canceled. 6 factored, so 30. 2i root 30. Okay. What if I had 3 this times the square root of negative 72? Well, 72 is 8 and 9. 2, 2, 2, 3, 3. What can I bring out? Pair of 2's and a pair of 3's, and there's already a 3 out there. So I bring out a 2 and a 3, which makes 6. And there's already a 3 out there, which makes, not 9, we're multiplying, 18. So 18i square root of 2. All right. Do you guys get that? Now, there's a really weird property with i's. Anytime you take a number on the number line and you add it to another number on the number line, then you just move, like you pick a number on the number line and you add 3. You move to the right 3. You subtract 6, you go left 6. Okay? So a real number plus a real number is a real number. But what if I had 4 plus 3i? That's all you can do. Right? We can't mix those. It's like saying you have 3 apples and 4 oranges. How many oranges do you have? They don't exist, right? They don't mix. They're different fruit. Okay? You could say, how much fruit do I have? And you could say, well, I have a total of 7 numbers, but they're not the same category, so we can't add them together. But I is referred to as the imaginary number. Not because it's pretend, but because it's not on the real number line. Okay? And when you pair an imaginary number and a real number, you get what we call a complex number. So this is a complex number, and it's treated like a single number. It has 2 parts, but it is one complex number. And we can actually add complex numbers together. So that's a 13. So if I take this number, 4 plus 3i, and I add it to 6 minus 13i, what's my new number? 4 plus 6 is 10, and 3i minus 13i, negative 10i. It's a negative, I didn't draw it very well, but it says negative 13i. Yeah, it doesn't look very good. That's my fault. Okay. What if I had 2 minus I plus negative 6 plus 5i? Two minus 6 is negative 4. And then negative 1 plus 5 is 4i. Wow. That happened twice in a row. Okay. You guys understand that? Okay. What if we did this? What do we do here? Oop, careful. It's a subtraction. 8 subtract 10, good. Negative 2. How'd you get plus 9? How do you subtract a negative? You add. Does anybody understand why that happens, or have you just memorized it? Just memorized it? So minus a negative is the same as adding, and I get plus 9i. Let me explain to you why that's the case. So let's say you're watching a movie on Netflix and you're fast forwarding or reversing. Okay. So let's say you want to go backwards. Well, you accidentally step on the remote and you push reverse. Okay. So your movie is now playing backwards. Well, if you go opposite from backwards, what direction will you be moving in? Forward. So this says you're 8 minutes into the movie, go back 10 minutes. Where do you end up? 2 minutes earlier than where you were to start. Okay. Well, if you're 6 minutes into the movie and you hit the reverse button and you backtrack, or sorry, you're 6 minutes into the movie and you want to go backwards 3 minutes, but you're going to do the opposite of backwards of 3 minutes. You actually go forward 3 minutes. Does that make sense? All right. You guys good with that? Okay, here's the other part. If I had an equation that said 12x plus 3yi is equal to 4 minus 6i. This looks really complicated, right? But we can't mix our x's and our y's. They're different fruit. We also can't mix our i's and our not i's. So we really only have, we have two parts hidden inside the same equation. This chunk contains no i's, and this chunk contains i's. So the question wants to know, what does x equal and what does y equal? Well, 12 times what is 4? 12 divided by 3 is 4. But 12 times what is 4? 1/3. So really, I'm just dividing by 12. 4 divided by 12 is 1/3. Okay? And then 3 times what is -6? Close. Divided by -2, but we're multiplying. -1/2. Okay? So let's say I have 5x minus 6i is equal to 10 minus 12, nope, minus 3yi. So we look at this and we say, okay, here are my real numbers. They have no i's in them. And here are my I numbers. What number does x have to be in order for this equation to be true? So 5 times what is 10? X equals 2. And then -3 times what is -6? It's also 2. You think you guys can handle that? So we are doing 5 through 30. Nope, all. These are really easy. So 4.6, 5 to 30, all.